Today what I'm going to be describing is a brief story, and I'm not going to go into great details at a certain point, but I'm going to be spending sufficient time to give you the message of the conceptual work that we are doing in our lab related to bioinspired synthesis of complex functional systems. And I think already you may have looked at this title and could have started to ask questions related to contradictory definition and terms and things like this. And therefore, in order to clarify all these issues, I will start to provide you the definition of every single word that I'm using in this title. And that doesn't necessarily mean that it's going to agree with everybody else's definition, but in order to avoid confusion, I'm going to provide definitions. So let me start by bioinspired synthesis. What do I mean? Because synthesis is getting by itself more complex lately. So bioinspired synthesis involves the synthesis that is related to how Mother Nature does synthesis. And Mother Nature does synthesis in two different steps. The first one is to make a molecule that will have a primary structure, that will have the structural information that is required to go to higher order of organization. That means fold into a secondary, tertiary, quaternary structure and provide ultimately a function through that process. And I'm going to give you a more detailed schematic illustration of what does this involve. It's a combination of organic chemistry and supramolecular chemistry. And then I will provide you examples of what is complex, what's the difference between complicated and complex. And from there on, we'll start discussing in more details everything else. So here it is what bioinspired synthesis is. If we decide, in biology, people are making functions through a very complex three-dimensional structure that is generated from aggregates of molecules that have a very precise conformation. And the way we learn some more in either organic chemistry or in biochemistry or in structural biology is that that is done via a very precise primary structure that will have the structural information required to fold into a secondary structure, tertiary, quaternary structure, and that's a mechanism by which you provide the function. So you would go immediately to all the textbook of chemistry and biochemistry, and you'll expect to figure out from somewhere how to do this. And let me confess and close this chapter eventually, and that could have been already the end of my lecture. There is no place that tells you how to do this, and we don't understand this process even for the simplest biological molecule that are peptides. And therefore, we have to first ask the question, why is that we cannot design a methodology via which we'll decide for a function, and then figure out what's the primary structure, and then follow this process and force them back. What is the problem in the field of chemistry that we don't understand, that we can do this approach in a very rational way? And that is illustrated here. What we don't understand in chemistry is the mechanism via which the structural information is transferred within molecules and in between molecules. That is, if we have a certain conformation in a molecule, and that conformation is transferred along the molecule to the other side of the molecule, and then from that particular molecule to another molecule, that mechanism is not understood because we don't understand the mechanism by which structural information is transferred in organic chemistry. The only thing that we know that there is a so-called allosteric regulation, but the detailed process of allosteric regulation is not understood. And therefore, both structural information and transfer of chirality information, it's the problem that is, I think, a topic that provides the biggest enigma of the chemistry in the 20th century and end of 19th century, since Emil Fischer started to get involved in these problems. And I think it will take a respectable part of the 21st century, if not the entire century, without making too much progress on this. So what is that we are going to do about it? And I will provide you our approach to this problem. So now let me define very quickly in a couple of words what means complex, and what's the difference between complex and complicated, and what are the two issues that are coming together when we go from complex to complicated. So complex systems are defined according to physicists, and here is a review from our laboratory that discusses in quite great level of details certain things related to complexity in organic systems. Complex systems display organization without a central organizing authority. That means, in the simplest words, that is a displaced organization without central organization authority means like a country running without a government. And the question is it better run that country without a government, or is better run by a government? And I think this issue is debatable. And I don't want to go into details, but I'll show you examples at the molecular level. So therefore, complex systems are characterized by these features. They are emerging, self-organizing, self-control that is similar to adaptation. So complex systems can adapt. And I think we are just going through a situation in which the economical situation is a complex system. The government has no clue how to fix it, and I think nobody in this world knows how to fix it. And it's a self-control process, and it's going to be self-fixed one day. We do not know when, unfortunately, but we hope that it will happen. The other feature that is characteristic of this complex system involves the following event, that in order to understand a complex system, we cannot get any information if we split it in small parts. And if we talk about a molecular complex system, we don't get any information about the complex system if we take a single molecule that is part of this complex system and understand it in greatest level of detail. That doesn't tell us anything about what that molecule role is in a complex system. We have to understand the overall system by itself. Now let's look at the complicated system, and there is a big difference. A classic example of complicated system is the Swiss watch that has many times many more parts than a complex system, but it can be understood in very great level of details by taking it apart, understanding the function of each individual part, putting it back together, and you can construct a Swiss-like watch, and you see all this mimic made in China and in Hong Kong that you can buy them for $5 rather than $5,000, and they're pretty good. And anybody can make them. So that's a different story. They do not adapt. That's the biggest difference in between the two systems, but their pieces can be understood in isolation, and therefore it is complicated, but it's not complex. So now let's look what's going on and what are complex systems available. This is the simplest complex system. It's complex biological system is a cell membrane, and it follows all the features that I was going to discuss, and the lecture that I will give will relate to a complex system from the cell membrane. But they exist all over. My view is that it's going to be much easier to understand the complex system at the molecular level rather than at the macroscopic level. And by macroscopic level, I can take the simplest one, the highway system. And we can look at it and see immediately what's the problem with the highway system. If we first construct this highway and we want to build another highway, we have to adapt to the presence of the first highway. You cannot do the design neglecting what the other highway is doing. And that's the case for internet, for society, for economics, for everything. You cannot disregard the economical situation in the United States and try to fix the economical situation in Europe. They are interconnected. So this is something very old in the field of molecular sciences, in the field of supramolecular sciences, at the macroscopic and at the molecular level. And let me provide the first definition that is extremely important for the rest of my lecture, and that is requiring to introduce a concept that is called Quasi Equivalence, and that is similar to self-control or adaptability. And this definition was provided by a gentleman called Klug, together with, at that time, Kasper, who was one of his postdocs. He was at Cavendish Laboratory. He's the father of structural biology and got a Nobel Prize for that topic. And in this publication, he introduced the concept of quasi-equivalence as a requirement in order to explain the self-assembly of icosahedral viruses. So here is a structure of an icosahedral virus, and this virus is made out of a single protein that is able to make pentamers or hexamers, and this combination of pentamer and hexamer derived from a single protein is providing the so-called icosahedral structure that is the simplest geometrical architecture that mimics a spherical object. Okay, so if we look at this, you can see that it was Leonardo da Vinci that did know about these principles of construction in the 15th century, and this is a story written by other people about him, that these general principles are extremely universal. This is the structure of C60. There is no way to avoid that quasi-equivalence. In order to build a C60, you need the pentagons that you see it here and the hexagons. And you can think about this structure as being the soccer ball that the Germans didn't know how to handle it very well a couple of days ago when they got beat by that little country that used to be part of Yugoslavia a while ago, and that is being used by architects, and in fact the name of C60 comes from these architects that is shown here. And we took this concept together with a gentleman whom I just visited this early morning, and we introduced it in the field of synthetic chemistry. So what is self-control? And from there on, I think we don't have any other definition that we should provide. Self-control is purposeful switching between more stable associable, and that's the most important thing to understand, and less stable associable quasi-equivalent conformation of identical proteins during the self-assembly of icosahedral viruses, and this is universal for everything. So what does it mean? That is the most stable conformation of an individual protein is not associable and has nothing to do with the conformation of the same protein during the self-assembly process or in an object generated by that protein. And this is a classic mistake that all organic chemists, including ourselves, are doing every day. So they are going to minimize and learn everything about the individual conformation of a molecule and trying subsequently to figure out what is that conformation doing during other processes. And that is incorrect, because the conformation that is associable is much less stable than the one that we generate by the analysis of an individual molecule. And I can use a very simple example to explain this. And that refers to the conformation of a single hand. And you can see that experiment illustrated here, basically, in a slightly different way. So if I'm looking through this audience, I see people using their hands in a non-associable and in an associable state. And everybody who's got a single hand, you can look at your own hand around. And if you look at your own hand, you are never going to hold one hand like this for a long time. You will collapse it by minimizing the free energy of the hand via exoenthalpic interaction in between the fingers. That's the most stable conformation of the hand, the most relaxed state. You can stay forever with a hand like this. But if you want to put two hands together, then there is no mechanism by which you will put these two hands together. So you need to go into a higher energy conformation, and this high energy conformation is not really known. I mean, I go into something, but when the hands come together and self-assembly provide the associable state of the hand or of the individual molecule, that's a conformation, and that's not known. I cannot duplicate it by having the hand out of the assembly state. I don't know exactly what's this conformation. I can take it, but I don't know exactly how it is. I need to analyze the two hands together to get that information. And that's provide the complexity of everything. Because when we go and we do the design, we are going to look at the attempts to design the conformation in the assembly state, and that is very difficult to generate. Okay, so in order to approach these problems, we also are involved in the design of synthetic methods and strategies for organic chemistry, supramolecular chemistry, and macromolecular chemistry. And I will just give you 2 examples here without going into any great details, just to have a flavor about what we do. And I'm not going to select examples from future experiments in which I use this, but you can find in our publication a lot of these things. So, for example, one topic that we are heavily involved with is nickel-catalyzed hormone cross-coupling reaction. And one example is borylation, Suzuki, Negishi, many other things. And I will explain why is that anybody wants to bother with nickel when everybody does this reaction with palladium. And the second one is single electron transfer organic reactions. A single electron transfer organic reaction, we take them to the polymerization chemistry for the very simple reason that that is a very low activation energy process. It can be zero activation energy process, and therefore you can manipulate reaction on a very, very mild reaction condition. That's again a biologically inspired organic reaction. It's scattered all over in organic chemistry done by biological systems. So let's look at the nickel catalyzed reaction and give you the reason and the rationale for why our group is involved in this. Many times students come to my office, and as I was discussing with Sigurd, I heard rumors that this university is running for certain things, and you write proposals and you don't get always all the money, and you need money to do research. It costs a lot of money, and experiments are quite depressing. The fraction of grants that is awarded is much lower than the fraction of students that would like to study, and therefore students are very shy when they come to my office and say, well, I need 25 grams of palladium, and I need to buy also a couple of Buckfall ligands that are even more expensive than palladium, and everybody knows that we don't have enough money unless I cut their stipend for 1 month or 2 months and cut their life story. So we decided to provide an option for this story, and that's going from palladium that's very expensive to one of the very inexpensive metals, and going from very fancy ligands to very inexpensive ligands. And if you are lucky, you are going to develop a methodology that's very efficient and cost-effective. And here is the reaction. That refers to the Suzuki reaction. So Suzuki reaction, I think, is very well known to everybody in this audience. I'm not going to go into any details. It involves the cross-coupling of a boronic acid with an aryl halide or pseudo-halide. And usually it involves palladium chemistry, expensive ligands, and so on and so forth. So in the first step of this reaction, you need to make the boronic acid. And while you don't have a problem when the R group attached to the aryl halide is something that's non-electrophilic, that doesn't react with a reagent that you are going to do the metallation step, and that could be butyl lithium. If you have electrophilic substituent, butyl lithium reacts selectively with electrophilic substituents, and you are going to get very low fraction of the boronic acid. The second reason is that borylation via this classic methodology is, again, a very tedious methodology. And people have developed palladium catalyzed reaction in which you are going to take an ester like this, except that is a tetraalkoxy diboron. That's very hard to make, very expensive. And again, you bump into palladium catalysis. You take tetraalkoxy diborane, you do a palladium catalyzed reaction, and you get a borylated product. So we wanted to figure out something very simple. And here it is. We take neopentyl glycol rather than pinacol. That is much easier to handle in this chemistry. We take the borane complex with DMS, mix the two in situ. You make this reagent, come with a palladium catalyst that is illustrated here, the one classic example. We call it mixed ligand concept. That is, there is a ligand that bounds on the nickel, and there is a second ligand that is different from the first one. This in excess in the reaction mixture. We don't understand yet all the details, but provides a very efficient catalytic system, and that can represent a two steps one pot borylation method that is efficient for aryl iodide, bromide, chloride, methylase, tosylates, and almost anything that's not activated. Both with electron donating and electron withdrawing groups. You can do even 3 steps one-pot reaction because you come with an aryl halide or aryl pseudo-halide under similar reaction condition and you get the cross-coupling reagent. So that's an example of methodology that we use in construction of molecules that I'm not going to get this, involved in the next part of the lecture. The second one is one-electron transfer chemistry. And this, again, bridges in between some organic methodologies and polymer chemistry methodologies. And that involves atom transfer radical addition. And that is something that has been transplanted from organic chemistry into polymer chemistry. And it's called ATRP, atom transfer radical polymerization. So what is that reaction believed to be? The following. A low oxidation state metal that is usually copper-1, take an alkyl halide and via a process that the author claimed to involve a homolytic bond cleavage followed by one electron transfer provides a radical. The copper-2 reagent that is generated in this step shifts the equilibrium towards the alkyl halide, but this requires a little bit of one of the fastest reaction and least desirable reaction to take place, that is bimolecular radical termination. If you get a little bit of bimolecular radical termination here, you get increase in the amount of copper-2, and that shifts the equilibrium towards this species, and very few radicals exist. And that can provide a very high chemoselectivity. Now, there is a problem with it. What's the problem? As soon as you mix copper-1 with a ligand, traces of oxygen will make it copper-2. As soon as you go from aryl iodides and bromides and chlorides, the bond strength in the homolytic bond cleavage part of the reaction is the rate constant for this cleavage, homolytic part of the reaction, is bond strength dependent. And therefore, you cannot activate any alkyl halide, and the reaction mixture needs to be very carefully purified. The reaction becomes very slow. The polymer at the end of the reaction is colored, or the organic reagents are very colored. You need to purify everything by column chromatography because copper-1 and copper-2 are colored reagents. And stoichiometric amount of copper-1 must be used in this reaction. So we change very little this reaction into a reaction mechanism that resembles somehow the difference in between SN1 and SN2. You get the same product, but the mechanistic pathway differs relatively substantially. So rather than using copper-1, we use copper-0. Copper-0 is a very good electron donor, and therefore transfer an electron to the alkyl halide that becomes a radical anion. Whether it's concerted or stepwise process is not important, but the halide leaves as a halide anion rather than homolytic bond cleavage. And there is a problem now. You generate copper-1, and you don't want copper-1 because there is no mechanism to put back the alkyl halide on the radical. And therefore, what we have found is that combination of solvents and ligands are providing a disproportionation of the copper-1 generated in situ back into copper-0 and copper-2. So this is it's a heterogeneous reaction. And heterogeneous catalysis is surface determined rather than concentration dependent. And therefore, the copper-0 that is generated in situ is atomic species that start agglomerating, but atomic species are much more reactive than the wire that you use or the 5-cent coins that you use in the reaction mixture. As a consequence, this is a very fast reaction. It doesn't require the purification of any reagents because copper-0 can consume first the oxygen from the reaction mixture. Is the classic BASF catalyst that is used in all glove boxes, and the process doesn't require the purification of the reagent at the end, and so on and so forth. So to conclude this part, I'm going to show you the real slide that is most significant about this methodology. You can make polymers that resemble proteins, but are not like proteins. So you are looking here at the Maldi-Toff spectrum of a polymer made via this methodology, and this is as good as polymer chemistry is able to do today. It's called the living radical polymerization. It provides polymer homologous species that have perfectly controlled structure of their chain ends. There is no structural defect in the polymer. And it's providing extremely narrow pole dispersity, and amplification of this Maldi-Toff is shown here. You don't see any second homologous species, but there is this number here that can be as low as 1.01. And that's the bad news of the entire story. A polymer that has a pole dispersity 1.01 is of no use for the rest of my lecture. The difference in between polymers with pole dispersity of 1.01 and proteins that have 1.00 is that 1.01 means about 3% of the chains from this reaction mixture have the desirable chain length, and the rest of 97 have higher molecular weight or lower molecular weight. And if you fold the protein into from different chain lengths, and you want to make, for example, an enzyme, you are going to create a mixture of 100 different enzymes. And that's of no help for this lecture. Therefore, we need to mimic in a very simple way, design a molecule that is synthetic, it's easy to generate, and that can mimic all the function of a peptide or protein. And that molecule can be explained by using this cartoon that is illustrated here. It starts with the concept of dendritic molecule that was elaborated in the late 70s in this institute by Professor Fockel. And this is not a molecule done by him, it's a molecule by Frechet. Nevertheless, 100% of the molecules around the world that are called dendritic molecule are of no help to us. We had to develop a very simple methodology to overcome some of the problems of these molecules. So we are looking at the Frechet dendritic molecule. That's a classic in this field, easy to make. It has one building block. You see a 3,5 substitution here, 2 building blocks, 3 building blocks. It's a branch molecule. And this molecule is either a liquid or a solid that is amorphous. What's the problem with it? It exhibits a 50-50 ratio between trans and gauche conformers of this benzyl ether. And this benzyl ether is the homologue of the peptide bond. The peptide bond, it's a little bit stiffer, but it still can rotate within ranges of temperature of the human body, for example. Nevertheless, proteins are equipped with a tool that can change the dynamic equilibrium between various conformers towards a single conformer. So they are looking at the introduction in this structure of that future. So let's look very carefully what we do. This is our molecule that mimics a protein. We have one repeat unit that is identical, 2 repeat units. The third repeat unit is slightly different. And then on the periphery, we place something that is dissimilar to the structure in the inner part of the molecule. And this combination of primary structure, together with the so-called hydrophobic effect or solvophobic effect, is sufficient to transform this molecule into a protein-like structure. It will select only one of the 2 conformers via this combination of tools, just like proteins are doing. So let's look, what did we develop in order to analyze these molecules? And we are going to develop libraries of molecules. We use a concept developed by Emil Fischer at the beginning of the last century. I think 1902, he put the iterative synthesis concept together, and since then we didn't do much progress in the field. Protection, deprotection chemistry, but we can make these molecules, and it's not important to show their structure. So we make organic molecules. If they self-assemble into certain objects, and I'm showing here a selection of some of the objects that this molecule self-assemble, and self-organize into certain lattices, then we can do retrostructural analysis of the lattices. That means if we solve this lattice and we know that it resembles this structure from here, and we have all the structural information, including densities, lattice dimension, and so on and so forth, we can calculate how many globular objects are in this lattice, how large is the globular object, and we can determine the conformation of the dendritic building block that is assembling into this globular object, and that's the equivalent of the secondary structure of the dendritic molecule, and this is the tertiary structure, and that's a quaternary structure. Okay? Now, what we do in the first instance, we will scan via very fast X-ray diffraction experiments, and I'm going to illustrate what do we get from these experiments. And then I'm going to select just one single molecule and do some experiments with this molecule. So here it is what we are doing. And this is an old piece of work. I could have selected something more recent, but that was more time-consuming. We make libraries, increase generation from 2 to 3 to 4. Again, details are not important. We maintain the inner part of the molecule identical. And in each of these columns, what we do different, we change the structure on the periphery. And it's not important what's the structure of the periphery. It's very important the outcome of the change in the structure on the periphery. So you see here, we increase the generation number, we get globular objects, slightly different sizes. We go and change the periphery, still globular object, but in this third column, we start getting rod-like objects. And the first instance, when we do very fast X-ray diffraction analysis, we do not know what's inside of this globular object. We know the conformation of the molecule, but we do not know whether that's a micellar-like structure with full freedom of the molecule to move, or it's a different structure that may resemble a protein. We go to the last set of molecule, and you see here a rod-like structure and the globular objects. Now let's change the inner part of the molecule from this library, from a 3-4-5 to a 3-4 building block. And you see that identical, identical. This became globular rather than rod-like. This is rod-like, this is globular. Not big difference. And now we will go to the constitutional isomeric library. We'll take this 3-4 and make it 3-5. And the question is, what do we expect to be the difference in between two constitutional isomers? And the simplest example I can ask the students in the back row, what's the difference in between ethanol and dimethyl ether? How many of you dare to have a drink once in a while from ethanol, and how many of you will go and have a dimethyl ether? And why is the difference? How can you see that difference by looking at this library? In principle, it's the conformation of the molecule that is responsible about everything. So let's look at this column only. The rest is not so important. But the libraries should look completely different. So you see no globular object with the exception of this one. And these two, it's identical, but this one changes the conformation. Here is globular, here is rod-like. So therefore, I'm just going to take this molecule in its two constitutional isomeric state and use it to conclude my lecture with all the experiments that I need from now on. However, before going there, I still have to go through a piece of history. And let me confess about history. And that's a kind of advice to how to read all the literature. I needed to figure out how to get information about these rod-like aggregates. And you expect that, well, I go to a book of structural biology or biochemistry, and it's going to tell me everything. And it doesn't tell you anything. In fact, you go to the original papers and you don't get very much. You have to go and read all the papers, for example, that are listed here, and then you will get surprising pieces of information related to how various things in the science have been developed in order to solve this problem. So here is one series of experiments. And I would like to bring the name of this gentleman called Linus Pauling. Linus Pauling was a very debatable scientific personality that had crazy ideas, and some of them are right, some of them are wrong. So at a certain point, Linus Pauling comes and says, certain peptides with specific primary structure must fold into a helical conformation, and the helical conformation eliminates the intermolecular hydrogen bonding and creates intramolecular hydrogen bonding that will stabilize the structure. Everybody in the world started to laugh with tears. Nobody could say that he was right or he was wrong. But everybody was laughing because they said, well, why would he have the courage to make this statement when structurally all the molecules he was claiming to form alpha helices were claimed to form ribbon-like structures and to be intermolecularly hydrogen bonded. So, peace on earth. He also advances a double helix model for DNA. Nobody could show whether he was right or he was wrong. And then this gentleman comes and writes a very important paper, more important than the paper that gave him the Nobel Prize. So Crick, Cochran, and Van are writing a paper and publish it in Acta Crystallographica, a journal I would never read. And it's called Helical Diffraction Theory. So what's a helical diffraction theory? These gentlemen come, and this paper is a lot of mathematics that nobody reads. If you are an organic chemist, they come and they say if you pull a fiber, and the fiber is highly oriented, and that fiber is made out of alpha helices, the X-ray pattern of that alpha helix fiber should be identical to this. That is a St. Andrew cross. They go into detailed calculations, and they will tell you the angle in between the cross and the meridian tells you the radius of the helix. That is the distance from the center of the helix to the high electron group of atoms that rotates to form the helix. The distance between these spots on the meridian gives you the pitch of the helix. That is the distance in between the high electron density spots. So with this story in your hands, you could have solved the double helical structure of DNA while being in kindergarten. In fact, Watson and Crick did it only when they were in their 20s or early 30s because there was no methodology around. Otherwise, they would have done it much earlier. In fact, this is the X-ray diffraction pattern that was taken away by Rosalind Franklin, who got it and threw it permanently because she didn't know what it meant. So immediately after this paper, Crick himself demonstrated that the alpha helices, so-called, suggested by Linus Pauling were correct, that the ribbon conformation of proteins were incorrect. Linus Pauling comes and demonstrates again that his alpha helices, by applying these methodologies, were indeed alpha helices. Watson and Crick are writing this paper that did not involve any hard work. In fact, involved only drinking a lot of beer at the pub across from Cavendish Laboratory, which I recommend the students to go there because you may get inspiration one day and you learn how to write an important piece of work without doing any hard work. So what they done, they took the X-ray diffractogram from Rosalind Franklin, who was trashing it, looked at it, had a big laugh, and showed that the double helix model of DNA proposed by Linus Pauling had to be inverted in order to get the radius of the helix that was provided by this X-ray diffractogram from Rosalind Franklin. So that's the only work that they done, and then build a model to show that look how nice it's this double helix. Since then, everybody's published and solved the helical structure in the literature only with the help of this methodology. There is nothing else in the meantime. So Watson himself solved the TMV that ultimately Klug solves definitively and gets a Nobel Prize for that piece of work. The structure of collagen was solved by using this same methodology. The amylose, the nanotube was shown to be helical by applying the same methodology. And we did the pain to spend about 10 years to look at this rod-like self-assembly structure made out of dendritic molecules and try to see what are they. Are they micellar structure? Or maybe incidentally they have some intracolumnar order that resemble what you see in protein. Now let me conclude what we have seen. And this is the cartoon that was very enthusiastic when we got it and very depressing at the same time. So we solved 14 structures. This is the art that Rosalind Franklin has done. You know, DNA, you cannot do a single crystal. You need to get a fiber that provides an X-ray diffractogram that is the same caliber, the same quality like a single crystal, and fiber can help you this. So by solving 14 structures and elaborating this methodology to incorporate the features that we had in this dendritic structure, we show that they can self-assemble in 9 2-helical structure, in 11 3-helical structure, triple 6-1 helical structure, triple 12-1 helical structure, triple 8-1, triple 9-1, octa 32-1, and I don't have room to show more of them. And in the meantime, we have demonstrated a lot of other structures. So there is a very nice news here, and there is a very sad news. This molecule displays a larger diversity of helical structure than protein, nucleic acid, and carbohydrates altogether. That's a bad news and a nice news at the same time. Why is that they display so large? Because there is more conformational freedom. You cannot freeze like in the peptide bond via hydrogen bonding and low rotational barrier, higher rotational barrier, a certain conformation. You just move permanently and you have more complex structures. But what we could do, basically, we could figure out a cartoon mechanism via which the helical structure are generated. And here is a cartoon that I'm going to use in the future part of the work. The all transconformation of the dendritic molecules are going to be able to form a disc-like conformation that will rotate. A hollow disc-like molecule will rotate, create a hollow center. A shade-like molecule, lampshade molecule, or crown conformation that could be supramolecular or molecular. It can be also hollow. They can form also a supramolecular helicine that resembles what's available in protein in alpha helices, and also that can be tilted and untilted, hollow and unhollow. And what is this helping us? Going through the libraries that I show you just one example of library, and having these details, we now can think about mimicking a complex system, or at least a fragment of it. And for example, if we want to design something that will be a channel that crosses the transmembrane, we would be able to do that by selecting this. If we want something else, we can again come to this library, and I will just select one example, the channel, nothing else. So the experiment that I will describe will refer to how to mimic a channel with very simple tools. And the cell membrane that is needed to do experiments with that channel, since I mentioned that we will discuss the two constitutional isomeric molecules, I will also show how to make a chiral container. And I will certainly provide some examples to nanomedicine, and a little bit I will discuss art at the molecular level. So let's take back this cell membrane and look at it. It looks very simple. So it's made out of two very important features. This is a barrier material. It's made out of phospholipids. And then you have the transmembrane proteins and carbohydrates, and you have the cholesterol, these yellow things that are incorporated there. And this is stable forever, for as long as we live. And it's a self-repairing system. Now, there is a problem with it, and that slows us down into solving many of the features. And what is that problem? Once you take away the transmembrane protein, carbohydrates, and cholesterol, and reassemble from the same phospholipid the cell membrane that's unstable and is polydispersed and is very hard to handle, and everybody wants to use it for drug delivery and as a model to understand the reconstruction of the cell membrane and the functions and so on and so forth. So let's first take one of these transmembrane protein, and there are very few that have been elucidated in the literature. And I will take one by Peter Agre that is called aquaporine. This is an hourglass-like channel. You can flip it upside down, and it provides the same function. And I will go very quickly what's the function. Forget about these details about the dimension and other things like this. The function that is extremely important is that provides 100% selectivity for the transport of water. Nothing else but water from the inner part to the outer part of the cell membrane. The molecules, however, move through this channel with a rate of 3 billions of molecules per channel per second. If you take and transplant and do a very simple calculation, each of us is filtering about in between 200 to 300 liters of water per day with this machinery. No mistake is done. That's why we can drink a lot of beer, regardless how good or bad it is, and a lot of wine. And, we don't really die as fast as we would have to die, because this is manipulated with a very high level of precision. No protons are passing. No protonated water or other ions are passing through this structure. The question that I'm going to raise, do we need such a complex structure to mimic these functions? And what is providing this function? So this is what we've done. We go to the library and we take one of the two constitutional isomers, the molecule that self-assembles into a rod-like structure that has a helical structure. And now we need to understand how to see the self-assembly process in solution and in solid state, and provide cooperative methodologies to get information about the overall structure of this molecule. So in order to aid our analysis process, what we do, we attach here at the alcohol part of the molecule a dipeptide. And that dipeptide we have selected. We got pure luck in this selection process. We selected tyrosine with alanine. The reason for doing this was that you can easily functionalize a phenol with a benzyl alcohol. You can manipulate the stereochemistry of these two amino acids. They are very cheap. You can make a lot of synthetic tyrosine that are not natural by putting other functionalities. You can play with the functional groups that are used as protecting groups and get a lot of information with a very fast way. So in fact, this was used as a tag. The tag is exactly what you get when you pass by the cashier when you go grocery shopping. The guy never opens your bag. He just scans it, and it tells how much you have to pay and what you have inside. So we wanted this dipeptide to tell us information about what's the conformation of this part of the molecule in various organic solvents. This methodology is available and applicable to all the nonpolar amino acids in combination with tyrosine. And I'm not going to discuss it. It's published work. But let's go and exemplify what is that we can do with this tag. So we are looking by NMR spectroscopy to a very simple series of experiments. We try to find out solvents that will take us from this dynamic equilibrium, 50-50 ratio between trans and gauche conformance of the benzyl ether, that creates a globular conformation into an all trans. So that's folding of the benzyl ether. And we look at a lot of different solvents and dilute concentration of this molecule in organic solvents. And when there is no change in the NMR spectrum as a function of temperature or concentration, it means we are dealing with this conformation. Because for steric reasons, there is no hydrogen bonding in between the dipeptide. If we see changes in the chemical shift, it means we flip this dynamic equilibrium into an all-trans conformation, just like folding into an alpha helix. And you can see here the solvent. That's deuterated cyclohexane, deuterated methyl cyclohexane, deuterated paraffin of any size will do this job. From this series of experiments, we can get a plot like this S shape that's telling us about everything about the mechanism of this process. It gives us all the kinetics and thermodynamics of this self-assembly process that is not important, however, for this discussion. The same information can be obtained from UV experiments, but now let's go and look at the next level of information that we generate from this. And that is ability of stereochemical information from the dipeptide to tell us things about this self-assembly process. So we attach the LL and the D dipeptides. They are certainly mirror images, very weak Cotton effects. We go in solvents that there is no self-assembly, and this Cotton effect doesn't change. Now we go in solvent that there is self-assembly that we have seen by NMR, and you see that this weak Cotton effect is not even visible. There is a dramatic amplification of the stereochemical information from the dipeptide, but is done via the aromatic part of the structure. This is temperature dependent, concentration dependent. You see that this ellipticity that had less than 50 units is amplified by about 5 orders of magnitude. we know that there is a transfer of stereochemical information from the dipeptide to the dendritic part of the molecule. We don't understand the mechanism. We can get a lot of information about the position in which you can place this stereochemical information and how fast and how efficient is the transfer of stereochemical information, but we don't understand the detailed mechanism. And the two structures are mirror images. You get again this S shape that you can use for the calculation of the kinetics and thermodynamics, and that's not important for this discussion. So we make the following assumption. There are two options, two hypotheses that we can put down. The first hypothesis is that there is transfer and amplification of spherical information or by this dipeptide, that is the dipeptide tells the dendritic molecule assembly into a helical structure if this amplification is provided by a helical structure. Or there is a second option, that the helical structure is generated from the non-chiral dendron, and the stereochemical information from the dipeptide tells the helical structure go left or right, go away from being racemic. And we demonstrated, without going into any detail, that second is the situation that, as you have seen by X-ray diffraction experiment, generated from non-chiral structure, we could see that, in fact, they are all chiral, except that they are racemic, and therefore the dipeptide just selects the sense of the helical conformation. Without going into any details, we show that the conformation of the assembly, it's the same in solution and in solid state. It's shape persistent. We solve the structure in solid state. I'm not going to spend time in describing that, but here is the structure that was solved by X-ray diffraction experiment. And the cartoon just shows how the molecules are coming together and what is that we could not learn from the analysis of the individual molecule. So you see that all transconformation of the dendron. The dipeptide is orthogonal to the dendron. The molecules come together and they cannot fill this empty spot from the middle. If you look very quickly, you see that the empty spot is surrounded by white dots that are the hydrogen from the Boc part of the protecting group and from the methyl part of the alanine, and therefore it must be a hollow center. And the first question that we are asking is, what can you do with this? And how does it look in higher level of detail? So you see, it's a hydrophobic pore. The hydrophilic part of the dipeptide is embedded in between hydrophobic and hydrophobic. Therefore, this was designed to self-assemble into the wall of the same membrane, because the wall of the same membrane resembles cyclohexane or a paraffin, and the water from the exterior of the cell membrane doesn't hurt this self-assembly process. So what's this good for? Here is the first technological application. How many of you visited this nice cathedral? You are close to France. When was it built? I give an award for a good answer. Anybody? Just a rough number. It's a very beautiful cathedral. The French claim it's the most beautiful cathedral around. So it was built about 1,000 years ago. How long did it take to construct it? Let me confess, 1,000 years ago, I just asked these guys at Technical University in Aachen and a couple of weeks ago at the Technical University in Munich, when were you guys built as a school of engineering? They said, oh, there was nothing around 1,000 years ago. I asked my first generation of graduate students in the United States, did you have computers 25 years ago? They said no, that therefore 1,000 years ago there was no computer to do the design of these buildings. Nevertheless, this building was built in the same amount of time as it took us to mimic only its rose window. So think about 20 years ago, 1,000 years ago. It took the same amount of time to construct all this cathedral that it took us to mimic its rose window. So this is what I write when I write a proposal to NSF or to other funding agency in the United States, and I tell people, look, how can you claim that we are so advanced in science when it took us as long time to mimic only the rose window with all the tools that we have 1,000 years later? And since we mimic this, we are trying to mimic more than one, and we don't increase the speed. It's not easier than the first one. Originally, I said, well, in the next year, we are going to finish all the churches from around the world, regardless of where they are and what centuries they were built. But we are not that good. So the second experiment that we done, it's a tough experiment that is providing the driving force for the last series of experiments that I will describe in my lecture. And that is, we make an artificial cell membrane. And that artificial cell membrane was made from phospholipids. The same phospholipids that are making the natural cell membrane. But as I mentioned, once you take the carbohydrates, the cholesterol, and the proteins, that artificial cell membrane is completely unstable. So therefore, all these experiments, we make a cell membrane, we put a dye inside. This dye is pH sensitive. It's changing its fluorescence when we change the pH inside of the cell membrane. Since this is a barrier material, if you change the pH outside of the cell membrane, you don't see any change in the fluorescence of the dye. However, these are painful experiments. You cannot do them as Watson and Crick have done their own experiment, sitting in a brewery, because this is not stable for more than 20 hours at the cold room temperature or refrigerator temperature. Therefore, students cannot go to drink beer in the evening, and not too many can be convinced to do these experiments. You've got to really work it fast, and you have to put the dye, then purify the exterior of this cell membrane from the dye that you used to purify. And you do these titration experiments in the exterior, and you see no change. Then you come with a natural channel that is non-selective, gramicidin. You add it in the reaction, in the water phase, that goes in the wall of the cell membrane, and immediately you can see the signature of the pH change in the exterior, because this dye allows files of water molecule to go in and out, and protons move through files of water molecule. Now we reconstruct our dendritic dipeptide channel, and you can see the signature of this transport of protons. We add a lot of gramicidin in the reaction mixture, and you can see that gramicidin is not more efficient than our channel. You can do a lot of additional experiments, and these are also difficult experiments. You make giant vesicles, and this is the blank experiment. You put it on the tip of a pipette, you change the osmotic pressure in the exterior, and what you see is that the vesicle is pushed inside of the pipette. It never comes out because it cannot equilibrate the osmotic pressure. There is no channel, and it's impermeable, this cell membrane. If you do this experiment with a channel from this dendritic dipeptide, you see that you can push it inside, but if you wait long enough, it's going to come back because water is going to come out to equilibrate the osmotic pressure. Then you can do additional experiments. NMR on lithium and sodium and chloride, and check for the ion transport. And to our surprise, in spite of the fact that the pore size is 14.5 angstrom, there is no transport. And that tells us a lot of information that are very hard to obtain by structural biologists. You don't really care about the pore size. Even if these ion pairs are solvated by water molecule, they are recognized by this structure, because transport through channels requires dissolvation. Ion pairs do not go through channels, only free ions go through channels. So the conclusion is that aquaporin selectivity is accessible by much simpler structural mimics, not with the same level of precision. Protons still pass, but ions of various kinds and other structures do not pass through hydrophobic channels. So the second experiment that I'm going to run very fast is the following. What I described so far is this experiment. We take this constitutional isomer, 4,3,4,3,5, and disassemble into this. We add the dipeptide and form this structure. Now the question is, if we take the constitutional isomeric structure that has only 3,4 substitution pattern here, that forms a globular object, we attach the same dipeptide here, what's going to happen to the molecule? Is going to be identical to this or slightly different? And here it is the way you do the analysis. You look at the X-ray diffraction experiment, this is electron density calculations, and combined with transmission electron experiments. I'm not going to go into any details, and compare the two lattices generated. This is the columns that are hollow, and this is a globular object. We cut the globular object and the column in the middle and put them side by side, and we say that they are almost identical. And they should be identical, because constitutional isomers have the same dimension, but they have completely different conformations. So we can look at the electron density reconstruction, and you see the alcohol has a non-hollow center. Once you put the dipeptide, you create the hollow center. You can fill it up with something. And then my students do the only experiment that I could predict that I shouldn't be doing, because I knew the result. And this is the advice I'm providing to the students from the back row or to the postdocs. Try once in a while not to use the wise advice of your advisor, okay? And you may have the chance to make a discovery. So here is the experiment. I said, don't do circular dichroism on this molecule, because a globular spherical object cannot amplify chirality, so you're not going to find anything. So here is a surprise. There is amplification of the chirality by a spherical object that cannot amplify chirality. And this work is done with some collaborators from the physics department. And these guys were so strong on what we discovered that they said, take away this amplification of chirality from the title. Don't send it to a big journal, just send it to JAX or something like this. And I'm still regretting that story, because we found very quickly after the explanation for everything. So you cannot amplify chirality by a spherical object. But I discovered, by trying to recall things from the days I was a child, how my grandmother was cutting or peeling an apple with a very simple knife, without any American or German technology. So if you peel an apple the way your grandmother was doing it, you are going to construct the so-called spherical helix. You can get a helical structure, a helical contour on the surface of the apple, and the apple peel has a helical conformation. Therefore, there should be a similar mechanism. And then I go back to all the scientific literature, and I find out in some very old work that a Portuguese who was trying to navigate from Portugal to India about 600 years ago was drawing a straight line from Portugal to India on the map, because they did not know that the Earth was circular. And a few hundred years later, somebody else took that map and made it in a circular object and figured out that that is the pathway of a so-called loxodrome, that helical spherics, or a spherical helix. That's been summarized in a journal of mathematical magazine or whatever, that and summarized in this book. This is the second edition. The first edition was published in 1930 or something like this. The problem is that there is no way you can convince a student to go to the library right now and get an old book and read it, because if it's not electronically available and the electronic version doesn't have the graphical abstract that is color, we'll never open that book. Okay, so I recommend that we still save some of these old books, because one day this damn computer that store all the libraries in the world is going to crash, and we will lose all the civilization that we developed in the past 2,000 years. So we asked a very simple question after that. Is this concept general? How easily can be adapted? And we took a molecule that nobody would claim that you can make a sphere out of it. That is a fragment of a graphite. The simplest fragment of a graphite is called a triphenylene, and triphenylene never want to form a spherical object. They will form columns. They pack one on top of each other at the pi stacking distance. We attach the dendritic molecule, and the object forms a helical structure immediately, a rod-like helix, and as a function of temperature forms a globular object that is also helical. And you can make the transition from this to this or from this to this via a lot of molecular recognition processes in addition to temperature, and demonstrate very easily that this is a chiral structure, that we can incorporate almost any functional group into chiral structure. And the summary of this concept is illustrated here. You can make chiral supramolecular sphere via this methodology, but you can make it via this methodology. This sphere is nothing but a very short helix. Amplification of chirality via these very short helices is less efficient than the amplification of the chirality through this long-range helical structure, but you still can amplify chirality. And there are a lot of applications that we are developing based on this concept. Now let's come back to what it should have been the first part of my lecture, and that is mimicking the simplest part of the transmembrane protein, and that is the phospholipid structure. And I'd like to make, once again, the summary of, there are two kinds of cell membranes. Contemporary cell membranes are complex systems, and then there are prebiotic cell membranes that are more primitive systems, but both are equipped with the same problems, the stability of these cell membranes. And to summarize this story, I would like to bring an example that was pursued in Germany by a very distinguished scientist that I had a lot of respect for. And I think that many of you may be very familiar with the name. That's Helmut Ringsdorf from University of Mainz, who retired quite a number of years ago. But he invested about 20 years of his life in an attempt to stabilize cell membrane made out of phospholipids and artificial amphiphilic molecules, and failed with all his work. He just never could do it. So the simplest approach that he could develop, he said, I'm going to make a phospholipid, have polymerizable group in the phospholipids, polymerize them, and that's going to stabilize the structure. They never got stable. So therefore, there was a need that we can do these experiments and generate a model that can be used to generate very stable cell membrane mimics. And here is the way we succeeded. And that's a paper that was published a couple of weeks ago. It's been highlighted here by everybody around the world, except including the chemical engineering news. And the concept is illustrated here. We made 11 libraries of what we call genus dendrimers. That is dendritic molecule that have a half of them that is hydrophilic, that can have alcohol on the periphery, or phospholipids, or whatever we want, or oligoxyethylene with alcohol, or with methyl ether, ethyl ether, and part of it is hydrophobic. We use an orthogonal approach to the synthesis of this molecule, so that if we make 5 different hydrophilic parts and 5 different hydrophobic parts, that I'm not going to go into details, you can make immediately 25 genus dendritic molecules. And we figure out that if you take an ethanol solution of any of these molecules and drop it in water, spontaneously form vesicles. And those vesicles are monodispersed by a combination of light scattering and by cryomicroscopy. That was easy to do. But then we had to figure out how stable are these. And those experiments took us about 3 to 4 years, because there is something that money cannot buy, and that is nothing but time. I keep telling my graduate students that that's something you never have to lose sight of, because you cannot buy back time. And you are never going to graduate or graduate with a much thinner PhD thesis that will give you a much thinner job in life. And that's what we've done. It took us a lot of time to figure out exactly what it is. So here is an example of cryo-electron microscopy. And you look at these molecules and you see that they have identical size, and that correlates very well with what you get from dynamic light scattering. You build a three-dimensional structure of these molecules and you see they have hollow center where there is only water. And you can do complementary experiments to cryomicroscopy. Cryomicroscopy is done on very small vesicles. They are monodispersed, very stable in time. But you can do giant vesicles that you can incorporate a hydrophilic dye in the interior, the water part of the molecule, and you see that you visualize it and you can see this. But you can incorporate a hydrophobic dye in the wall of the structure, and you can measure the thickness of the wall. And to our surprise, the thickness of the wall of these molecules is more or less that of the phospholipids of the cell membrane. Therefore, we can do structures that function and provide mimics of biological cell membranes. We can do giant vesicles that we use to attach to a pipette and do mechanical properties of this vesicle, and figure out that they are better than the mechanical properties of the commercial vesicles that are loaded with 50% cholesterol, and nobody wants to incorporate in their own body cholesterol, but all the delivery of drugs is generated by these vesicles. So here is an experiment. So the features of these two groups of molecules, liposomes that are made from phospholipids, and the one that are generated from polymers or blockopolymers, are that the second group is stable, they are polydispersed, require tedious purification, but they are toxic to cell. These are unstable and polydispersed, and they need to be fractionated through very tedious processes. Our molecules are monodispersed, are impermeable. Impermeability is as good as of the best molecules, stable in a diversity of aqueous media, and in time are biocompatible, exhibit the thickness of phospholipid liposomes, great diversity of functionalization, and excellent mechanical properties. Not only that they form vesicles, but they form the larger diversity of additional complex structure exhibited by any natural or synthetic class of molecules, including phospholipids and blockopolymers. And some of the structures are illustrated here. They form polygonal vesicles, they form cubic structures, and you see the three-dimensional reconstruction of this structure. They form vesicles that are filled, and they are micellar structure. They form rod-like vesicles. They form tubular and ribbon-like helical field structure. They form toroidal structure and many, many other. You can functionalize their periphery with a large variety of functional groups, and that provides access to nanomedicine, particularly not only the delivery of drugs, but also to what is called theranostics, that is detection and treatment of diseases via these molecules, because you can visualize the cells and deliver immediately the cell. You can demonstrate that these molecules can be co-assembled with non-dye-tagged Janus dendrimers and non-dye-tagged phospholipids and with blockopolymers, and you stabilize them with very little amount of the Janus dendrimer. And for the girls from our group, we have already started to develop new things in cosmetics, so that they are going to be happy about what we generated for the other people. So what else we have done with them? We have developed methodologies to test what molecules are going to assemble like this and what not. And that work is done in collaboration with a large group of experts. So these are the co-authors on this paper. They aren't more than 22 or 21, but they are very diversified, and it's very hard to get these people together because everybody has his own interest in addition to our own interest. So we have Mike Klein with his people that are doing the simulation via computer simulation. And we've done a series of experiments in which we gave him molecules that we know what they form and molecules that we do not know, to see how good can he get. And I think he's getting to the point to predict what molecules are going to form the structure and what not. And I'm going to show you a glance of some experiments. So we take a molecular solution of this molecule, and you are looking here through some fragments in picoseconds. The molecule self-assembly into a vesicle by showing it the bilayer structure first, the unilamellar bilayer structure, and then forms vesicles. And let me show an example. This is how the molecules come together, and you see the complexity in part of the structure. The conformation of the molecule doesn't have anything to do with the conformation of the individual molecule. The molecules first get hydrated with water, and the hydrated molecule is different from the non-hydrated molecule, and ultimately making a bilayer, but this bilayer is only a fragment of the vesicle. And I can do an additional experiment in which we look at the entire structure that is generated. You can see how the molecules are struggling. This is a slow-down process through the computer simulation, and we'll generate the closed vesicle. You see, these are predictable structural defects, and the vesicle, it's exactly what it's a natural vesicle. What's very interesting is that we could incorporate channels, natural channels in this structure that cannot be incorporated into other structure unless the thickness of this cell membrane is exactly that of the phospholipid. And this molecule has a structure close to that of the phospholipid. So here I'd like to stop and thank the people that have done the work. I labeled them in two different colors. The one in red are struggling just like me because they are academics and they write more proposals and do more typing than my secretary used to do 25 years ago. Therefore, they start as being handicapped. They are computer secretaries. And the one in blue are national laboratories, industrial laboratories, and so on and so forth. And I would like to stop here and thank you very much for your attention.